So I think we can stop there just see if there's any questions that we can take. If anyone has any questions or comments, feel free to drop them now, and then otherwise we'll continue on into the kind of basics of building your own PyPSA network. Okay, no questions. Hopefully everyone can hear me and I haven't been presenting to myself for the last while. Okay. So what we're going to do is just work through a set of examples that will help you build your kind of first PyPSA network from scratch and just
Peter,
understand. Yes.
I'm sorry, there is one question. If you just look at the questions that were typed up there in the comments.
Boy, don't you want to just post it?
It said it's from Gregory Ireland. It says, how does your PyPSA RSA work fit in with the PyPSA meets Earth work?
Yes, great question. So when we started the PyPSA RSA modeling, at the time we obviously looked at all the available models that were that we had access to at the time. And there was an existing model of the South African power network called PyPSA ZA. And PyPSA Earth at the time had just started and was getting off the ground and starting to gain some momentum. Ultimately, it would be great to not have multiple different models that we can kind of merge the same functionality, ultimately, hopefully back to PyPSA Earth. In our experience, what we found was that the kind of PyPSA Europe, PyPSA Earth models are designed to be quite generic and easily replicable across different regions. But it didn't have the kind of level of detail that we needed or the functionality in the model to kind of do a very deep dive on the South African network. So when we started the work, for example, there was no ability to do perfect foresight capacity expansion planning in PyPSA Earth. It was limited to kind of like a single node, a single period in time. So about at that time, we then started adding in all the functionality that we wanted from the network to be comparable with Plexos. So the first thing we added was perfect foresight expansion, and then just a lot more specific detail about the South African power system. So subsequently, what's happened is, I think, is that the development on PyPSA Earth has continued. There was just a lot of functionality that we weren't kind of using all that much, like the clustering of the network, for example. We were using we found it easier to stick within the ESCOM defined areas because there's a lot more information. But one of the things we're quite keen to do is do a benchmarking exercise between the PyPSA RSA model and the PyPSA Earth model, and just see kind of how these two models are comparing to each other, and look at if there's any additional data that we can merge from our model for the region back into PyPSA Earth, and vice versa as well, if to see how the model compares to kind of our own modeling approach. You'll see when we get to the talking through the scenarios and the approach to the PyPSA RSA model in next week in a bit more detail, we found some tweaks and changes to the overall workflow of those models that we found helped us a lot more when we wanted to set up and run quite a large range of scenarios with different parameters and how they're all varying and different costs. And so we've kind of come up with our own interface, mainly Excel based, that feeds into the model. So for better or worse, but we found that it helped us internally in terms of a bit more of a streamlined way to set up scenarios and run them.
There's an additional question from Garth. He asks, does PyPSA run on a Mac?
Yes, it does. So we'll get to the kind of installation and system requirements now. It does. The most important thing to bear in mind is that depending on the type of model that you want to solve is computational resources. So any Python-based program in Mac, Windows, or Ubuntu, we can use Python and PyPSA in it, but you're not going to be able to solve a national power system model with multiple decades of expansion, for example, on a laptop. We use just a normal desktop for our calculations. It's just a kind of a recent i7 or i9. But the most important thing is RAM. So our models are topping out at just under 128 gigs of RAM for some of the scenarios that we run. So that's just not going to be feasible to solve on a laptop. If it's smaller networks and that, then most definitely possible to solve on a laptop. You don't need a GPU at this point, so everything is more CPU bound, but RAM is the biggest limitation.
An additional question from Stephen Peter. He asks, would PyPSA be an appropriate tool for smaller modeling scenarios, for example, available capacity at a particular 400 kVA transmission line?
Yes, so I mean, I think we'd have to learn a bit more about the exact problem that you're trying to solve. But my gut feel is that, yeah, definitely possible. And we've managed to do a fair amount of those kind of studies. You can do, like, for example, if you have a PyPSA network, we'll get into the detail actually in a few slides, but you can have passive components, whether it's transformers or lines, for example, and you can give them different impedances, and PyPSA will take into account Kirchhoff voltage and current laws within the constraints that you solve. So there is some level of modeling that you can do in that space, generation and the transmission between different areas, but it's not going to be the kind of very high resolution transient stability type analyses that you would do in DigSilent, for example. And so it's kind of a step up from that in detail. So basically, if you're starting with a kind of a completely clean slate, you've heard about PyPSA, you're very interested, and now what is the next question? So this slide, and we will make these slides available, all these links would be my go-tos where you want to start to learn about energy system planning, PyPSA, some of the functionality, etc. So a good starting point is always to go, and with most of these open source libraries, is to go to something called Read the Docs, where it's kind of like an automatically generated guide to that library. So I'm going to just try flip here quick to let's move this. Okay, so if you go to the basic Read the Docs for PyPSA, so you can follow the link on the slide that I have there. It'll provide some great introduction documentation, how to go through the installation of the different libraries. So this will give you a walkthrough in quite a lot of detail, and kind of how you can approach all the different installations. And then once you've got that up and running, then more importantly, there's some great worked examples. So definitely you can make the effort and kind of go through all of these worked examples that are available, which kind of the worked examples are very, very small, high level. So you won't get a lot of detail out of them, but it helps you to start to understand some of the different functionality within the model. So for example, here's an example on LinoPy and how you can add custom constraints, etc. And all of this, I'll show you how to get it from GitHub. You can have these as Jupyter notebooks, so it's all done for you, and really you just have to run it, and then you can start to interact with the network object. So once you've kind of gone through some of the initial read the docs, I highly recommend this free course by Fabian Neumann. And there's also a really good series of lectures by Tom Brown. So they kind of from the Technical University of Berlin, and they're really the main developers of PyPSA. And so there's some really great content here, which is kind of a short course that will take you through all you need to know, not only for PyPSA, but also in terms of some more broader energy planning and how you could do some capacity expansion planning with PyPSA. So once you've done some of the initial examples, then highly recommend working through this course, which is kind of a little bit more detail, and it does everything from up to, there's some simple sector coupling examples, and then there's also some visualization. So how you can load a network, how you can start to plot different powers, how you can do some kind of spatial mapping of generation, etc. So really useful resource here to use. Then there's a link to our GitHub where we have been placing the PyPSA RSA model, and then over here you'll be able to we're a little bit behind on updating some of the text, but that'll come soon. But our actual model sits here, and there is some supplementary data that you will need in order to run the model, and we'll talk through what you need to download from where, and then we will make some data available as well, some pre-processed data. So that's kind of the basic up to our model. Then there's different, like Greg mentioned, there's some bigger PyPSA models that are out there. So there's PyPSA Europe and PyPSA Earth are the two main models, and there's a lot of info and details there. Once you start working with the model and you kind of get stuck, there's a really great Google group for PyPSA, and then lots of people ask different questions here, and you can also search. So for example, if we wanted to know about reserve margin, there's a lot of people asking questions around how you would implement reserve margin, spinning reserve, etc. So it's another great resource to look at. In terms of a bit more interactive as well, highly recommend getting onto Discord. So a lot of open source development and discussions. It's kind of like a chat platform, and especially the PyPSA Earth Discord server is there's also support kind of different queries. Highly recommend getting onto that Discord channel as well. Then finally, there are some video tutorials available on YouTube. So the PyPSA Earth channel has some great YouTube tutorials, and there's also some basic tutorials on PyPSA Europe and how to use that model. Ingeborg, sorry, can I just confirm you can hear me? See, I'm getting a network issue.
I can hear you okay, but you are freezing a little bit.
Oh gosh. Okay. If it gets too bad, I'll try to flip onto my onto another network. So just interrupt me if it gets unusable. Okay, so if we look at then where do you start? So the the first step is that you need something called an IDE, or an integrated development environment. And that's really just the place where you are going to write your scripts, you're going to make changes, you're going to debug when you find issues, and you're going to run your code. So we highly, highly recommend using Visual Studio Code. There are a lot of different Python development environments that are out there, but I personally think Visual Studio Code is excellent. There's a lot of add-ins that just make life easier. In terms of the question, in terms of operating system, again, you can use Ubuntu or Mac. Those are really the preferable development environments, and they offer a lot better performance, and library compatibility especially is a big thing compared to Windows. So often we find that the Python libraries for Windows are not as updated in some cases, or there's certain functionality that doesn't exist, or it's much harder to install a solver to really doing everything in Ubuntu. So all hope is not lost though. If you are a Windows user, we highly recommend that you install something called WSL2. So WSL is essentially Windows subsystem for Linux. No, well, anyway, it basically allows you to run a very lightweight virtual machine of Linux on your Windows machine. And the crazy thing is, often we find some Python libraries running in WSL on Windows are faster than running the equivalent Windows library on Windows. So the performance knock is not significant. It takes a little bit of setup, and what I've done is include 2 great installation guides that will take you through how you can set up WSL, what are some of the things you need to watch out for, and basically how you can install Ubuntu to run on Windows. There are sometimes a few sort of challenges along the way of getting the Ubuntu installation and everything going, but I know Microsoft has ironed out quite a lot of those and made it a lot more simple to install these days. The one thing just to point out is that you often have to change some of your update and security settings to make sure that you can update the WSL kernel before it will let you properly install the version of Ubuntu that you have. So here are the 2 links that you can follow. In terms of installation of Python itself, so now you've got your kind of raw version of Ubuntu, whether it's either natively under Ubuntu, or if it's running on WSL2, and now you need to install Python. So there's various sort of package managers that you can use. So at the moment, I put the link here for Anaconda, but there are different options, like Miniconda, for example, is just a more lightweight version of that. So you would follow this link. You're going to download a shell file, and then within your terminal, you're going to run just 2 commands that will then allow you to install that. So you've got to change your folder to wherever you've downloaded the shell file, and then you can run it and just reinitialize it, and then you'll have essentially Anaconda installed on your machine. Final step of what you also want to do is look at GitHub Desktop, and I'll show you how you can basically use that to get access to different Git repositories, and how you can start to pull code from the different libraries that are out there. In terms of some different extensions that you're going to want to install, so once you're in Visual Studio Code, you can see this little icon here for extensions. And if you're using WSL, you want to make sure that you install this WSL extension, and that allows you to essentially use your Ubuntu terminal from Visual Studio Code. And then you also want to install your Jupyter notebooks, well, the support for Jupyter notebooks, and then just some of the IntelliSense for Python code. So these are some extensions that you're going to want to install. So in terms of a very basic setup procedure, I'll take you through a quick walkthrough now. But basically within your terminal, let's say we want to work on something called a PyPSA demo. And the only library that we're going to need then is PyPSA itself for the small example. What you're going to want to do is create something called a virtual environment. And that's really, it creates kind of a distinct ring-fenced area for different libraries. So what happens if you have all your different libraries in a single environment, what can happen is there'll be conflicts. So your one library needs a certain version of this package, but another library needs a different version of that package. And then because of these conflicts, you can't install all the correct libraries that you need. So creating a virtual environment allows you to install all of that information then into a single virtual environment that's really for each project. So if we're going to now create something called our PyPSA demo, we're going to, first thing you're going to want to do is make sure you have your condas updated. So you'd run the script in the terminal, and then you can create a new environment called PyPSA demo. You want to activate that environment. So I'll show that this conda activate just then flips to that environment. Just make sure that pip is installed. And then you can use pip to install the latest branch directly from GitHub. So this set of code will get you to the point where you have a basic PyPSA environment installed, and you can do some small demos that we're going to go through now. If you want to, when you want to get to the PyPSA RSA model, it's a little bit more involved because there's a lot of different packages that have to be installed. So the first thing is you want to clone the GitHub repository, which we'll show, and then you want to change directory to the path called environments, and then you can create your conda environment using the script. And what it will do is it will automatically tell it all the different lists of packages that you need to have installed in order to run the PyPSA RSA model. So that was a lot of kind of background information, but what are the kind of key aspects of an actual PyPSA model? So there's a few different concepts that if we're going to set it up. So the first is energy carriers. So that's typically referring to the primary energy source. So whether it's kind of for fossil fuels, if it's coal, liquid fuels, gas, etc. And that's often used to keep track of what the emissions are associated with those different kinds of generators. Then you have your renewable generators. So you might have solar and wind as different carriers. Then the carriers get converted into energy through a generator, and those are connected to a single bus. So the bus is a node essentially where an energy balance has to take place. So you have different generation load, and then you have energy that can be transmitted in or out of a bus. So you can have multiple generators connected to a bus, and then there are different passive power flow components. So there are lines and transformers. So a line connects one bus to another bus that's at the same voltage level. If you have buses that are at different voltage levels, then obviously you need a transformer component that sits in between them. These are passive power flow components. So you're not basically the power is going to flow based on impedance, but you also get kind of more active power flow components where you can enforce a specific flow. And these are almost more like HVDC components. So you have something called a link. So again, a link can be used purely within the electricity sector, where you go from connecting one bus to another bus through your link. But then a link can also represent a conversion into a different energy carrier. So as I said earlier, PyPSA can be used for more sector-coupled models where essentially you can have not only your power sector, but the connection, for example, to a hydrogen network. So a link can also take energy from a bus of a specific carrier, and it can convert it into a different carrier. So for example, here a link would represent an electrolyzer, and you put in electricity, and there's some kind of conversion ratio that happens, and so much electricity then gets converted into hydrogen. Then the kind of next category that you have are really loads. So a load can sit at a bus, and it withdraws power from the network. It's also possible to model negative generators. So a negative generator can represent a load, but it gives you a bit more flexibility. So for example, you can have price sensitive loads by modeling that through a negative generator. Then finally, you can also have storage devices or stores as well. So a storage unit itself is, you can think of as an integrated system. So if we focus on batteries, it includes the power conversion electronics to go from AC to DC and charge the battery. Then there's the actual storage component, so the energy storage component itself, and then the power electronics to then discharge the battery again. So a storage unit has all of that built into one, but there are more fundamental units called stores, which then is just purely the storage component, and typically you would use that with links. So you have a link that converts the energy into the storage medium. You have the storage medium as a store, and then you have a link that converts that stored energy back to your primary medium again. So you can, if you go through the documentation, there's a lot of description around the maths, but ultimately the maths is really simple. It's sort of all linear equations. You can dig a bit deeper into kind of graph theory and some of the power flow in networks if you want to. But really, it's all about matching supply and demand at a bus. And then, so energy into the bus, energy generated, energy to the load, and that must all balance between that and energy out of the bus. So all the model is doing is make sure it's balancing all of these constraints in every hour that you are looking at. And as I said, you can include some detail around how the grid is modeled. So if we start off with what are some of the key components of a generator, essentially you have a generator object and you have to populate it with certain amounts of input data. Some of it is optional and some of it is mandatory. But typically this is kind of what you would use to define a generator. So you have a name, you have the bus that the generator is connected to, you have the carrier. So for example, if it's solar, wind, or coal, you have a sign. So positive means that it's a generator at a bus. Negative means that it could be representing a load, for example. Then you have something called P_nom. So P nominal is the installed capacity of that generator. And that tells you really what your maximum power output can be. And then there's something called P_nom extendable. So if this is by default set to false, but if it's set to true, you're not fixing the capacity, you're allowing the optimization to see if it can install more capacity and what the optimal capacity is that you need. Then you have some parameters that you might want to specify around min and max. So if you say that, and typically you would use this around build limits, so you can optimize the capacity, but it can only be between 50 and 100 megawatts. That's where you would use P_nom min and max. If you're doing capacity expansion planning over time, you want to define something called the build year. So that's the commercial operation. And it does typically happen. The capacity then is assumed from the 1st of January in that year. But within the PyPSA RSA model, we have got a functionality where you can phase in capacity over the course of the first year. You also then have lifetime of the asset, and then you have cost information. So, apologies. So this capital cost here, it's a little bit of a, the term capital cost, it's actually the annualized cost. So it's the annualized cost of the CapEx plus the fixed O&M cost. So don't be confused by the fact that it says capital, and you have to work out the annualized cost yourself. So I'll show you, and you just use a quick capital recovery factor, for example, to turn the capital cost into an annualized cost. Then you have marginal costs. So that's the marginal cost of production in rands per kilowatt hour. And this can be a fixed number, or it can be variable, but that does increase computational costs. Efficiency is really, it affects mostly, so for example, if you have a coal generator and you have an efficiency, the efficiency and the carrier are used to really look at how much primary energy is required to generate a megawatt hour. And you can define that as a heat rate, and it will get converted into efficiency in the PyPSA RSA model. And then finally, a very important parameter when you're modeling, especially variable generators, is how that power is allowed to vary in every hour of the model. So Pmax PU is so this is just a per unit number. And typically it can be just a static number. So you could say like Pmax PU equals 0.5. So that means that in any hour of your simulation that you run, the generator can't exceed more than 50% of its power output. And then typically how you would model wind and solar is you have a time varying series that then governs how that renewable energy is available. And that would get set as a Pmax PU for that number. Finally, just another example for storage units. Storage units really has a lot of the same parameters. It's got an efficiency, charge, and discharge. So that's your charging and discharging cycle efficiency. And with a storage unit, typically what you have is a fixed ratio between power and energy. So for example, a 4-hour battery would mean that you can discharge the battery at maximum capacity or maximum power output for 4 hours. So that's what the max hours is used to specify. Then the capital cost that you specify, it's very important that it's on a rand per megawatt hour, rand per megawatt basis. So often you will have storage capital costs on a rand per megawatt hour, but you have to make sure that you use the max hours with the relationship between megawatt hours and megawatts. So your capital cost for a storage unit is in rands per megawatt.